So the theory behind this lab is basically all about Huygens principle, and so we have plane waves that are made up of infinitesimally amounts of spherical wave emitters, and once the plane waves hit the physical aperture of the slit, these spherical emitters will cause the circular wave pattern, which will then cause interference, which is why we get the diffraction patterns.
Using this equation to calculate Z effective for the single slit apertures, we found a Z effective of 1.5 millimeters, 6.3 millimeters, 25.3 millimeters, and 101 millimeters, respectively, for each slit.
You can see that the light is elongated along the vertical axis when we are in the Fresnel region. Once we move towards the Fraunhofer region, we can see that the light is compressing a little bit towards the horizontal, and once we hit the Fraunhofer region, we see that it's completely elongated along the horizontal, and as we continue farther away from the detector, we continue into the Fraunhofer region. As the slits decrease in width, the Fraunhofer diffraction increases in distortion along the horizontal axis.
For double slit apertures, as length of the slit increases, width of the Fraunhofer pattern decreases. As separation of the aperture increases, width of the Fraunhofer pattern increases. Using the sinc squared function for the rectangular aperture and the sombrero squared function for the spherical aperture, we found an I over I naught for the first maximum of 0.0585 for the rectangular and a second maximum of 0.031. For the circular, we found 0.034 and 0.02, giving us a 30% error, 93.8% error, 94.3% error, and a 376% error. Estimating locations of the two minima and the maxima, we found that the maxima was located closest symmetrically between the two minima. Estimating locations of the two minima and the maxima for the circular aperture, we found that the maxima was located close to symmetrically in between the two minima.